So chapter 5 is resampling methods. So I think this is good for just the one day. So we will study the two concepts. One is the cross-validation, and the other is the Bootstrap. So how many of them have heard of cross-validation or have used cross-validation before? Uh, 50-30 we covered or not covered. I'm not exactly sure. 68-40 maybe we covered, but at least it's not the main topic.
Cross-validation.
Sorry?
We did cross-validation in 50-30 for sure, using training and test sets.
Oh, training and test, right? So the cross-validation, we have the yeah. So the multiple trial of the training test approach is cross-validation. How about the Bootstrap? The Bootstrap, at least it is covered in 50-30, somewhat, not heavily. So these techniques are especially good to evaluate the variability. So these two are in common in terms of the method, because both methods are resampling methods. So what is the resampling method? Resampling method means that we sample from the sample. So suppose we have data, for example, the 5.0, 6.3, 7.1, 6.1, 4.8. So one problem is that we treat numbers as realization of random variables, but once you observe the data, we don't have any randomness. So you can take the average, for example, the X bar. What is X bar? About 6. So 0.3, -1, 1.1, 0.1, -1.2 from 6. And okay, so this is 0, so -0.7. So divided by 5 is -1.4. So the 5.68 is the average. But okay, so these are realization of random variables. So if we have another 5 observations, then we have different X bar. But since we have already taken average of 5 observations, we don't have any variability in X bar. So we don't know how reliable this X bar is. So resampling method means that we sample from this sample. For example, we take the 3 observations from this sample. Then the way to sample 3 observations is somewhat random. So we replicate some randomness. So then we can do several things. And yeah, so that is the concept of resampling methods. So once again, so the problem about statistical inference is once you observe the data, everything is fixed. So we don't have any randomness, but we artificially create some randomness to see how reliable or how stable the result is. And cross-validation. Cross-validation is a method to evaluate test errors with multiple randomized training and test sets. So mostly in, I think 50-30, we divide the data set into training and a test and to do something. Or the data competition, usually we have training and a test set. But here we have the multiple randomized training and a test set. So we make training set and a test set. Then we use the same data, we make different the subsets as training set and the remaining observations as test set, and so on. So that is 5.1. And Bootstrap. The Bootstrap is a method to estimate the distribution of parameter estimates with multiple sampling from the data set. So Bootstrap means, yeah, so So we do multiple sampling. So for example, we take 3 observations from the data set here. Then the next time that we choose the different 3 observations, for example, the 6.3 and the 6.1 and 4.8 or something like that. So if we choose different data set, we have different X bar for these 3 observations. The 5.0, 6.3, 6.1. The average is 5.8. And these 3 observations, 6.3, 6.1, and 4.8, our average is maybe 5.73. So we have slightly different ones. So we can now evaluate the variability of X bar. So that is the basic idea of the Bootstrap. We have slightly different formulation exactly, but we will cover it in 5.2. And a review from 5030 or 6840 or other courses, the validation set approach. So the simplest method to evaluate the prediction performance is the validation set approach. So we have the data set and we divide it into 2 parts. So this is just a random process. So I'm not sure that did you do the quizzes for the last lecture? Not yet.
I haven't yet.
Yeah, you haven't. Anyone have done
not
that?
yet.
No,
No, not yet. Okay. Okay. Yeah. So for the last lecture, that I asked you to divide the data set into 2 parts. The quizzes uses the Boston data set. The Boston data set is the real estate data set for 506 towns, and I ask you to divide the data set into odd numbered lines and even numbered lines. So we have 1 to 506, but the training set as 1, 3, 5, 7, 505. This is training set, and the test set is the 2nd line, 4th line, 6th line, and the 506th line. So in this way, it's almost random. I mean, it's systematic, so it's not exactly random, but it's important to randomize this set. Actually, I was thinking to divide the data set into just the first 253 observations and the last 500 to 253 observations. But in this way, actually, we have a large bias. Actually, the first data set have the more expensive towns, and the second data has the inexpensive towns. So we have some bias. So it's important to randomize it. So we don't have any systematic, I mean, don't have any bias in the training and test set. That is important. Yeah, so the point is that, okay, so we make a training set and a test set, training. And we estimate model from training set. So suppose the training set includes the variable x and y, then we estimate y is equal to beta naught hat plus beta 1 hat from training set. Then we apply test set. So test set also have the x and y. Then we estimate, I mean, we predict y value by beta naught hat plus beta 1 hat times x. So these estimates are obtained from the training set only. So these estimates are from training set. Okay. Then we use the test set to evaluate the performance. So we explain the why. So the point is that if you estimate with the training set, then of course these parameters are good for training data. So it's not really a prediction, but just we are fitting model. But to evaluate prediction performance, that we have to use the new data set. So that is the test set. So we use the estimated parameter from the training set, then we evaluate the performance. So evaluate performance. Prediction performance. So this is the training test approach. But the most fundamental weakness in a validation set approach is the trade-off between accuracy of statistical model and accuracy of the test error. So estimated model, so accuracy, yeah. Estimated model is more accurate when training set is large. But the test error is less accurate since the remaining test error, the remaining test set is small. Or if you make a training set smaller, then estimation is not accurate. Then we have many observations to test. So test itself is the more reliable. So typically, suppose we have 100 observations. How many observations should be in the training set and how many observations should be in the test set? If we make 95 observations in a training set, we have pretty accurate model, but we only have 5 observations to test. So test performance really depends on the specific characteristics of these 5 observations. So test performance, the evaluation of test performance isn't really reliable. Or if you only have 5 observations in the training set, of course, you cannot estimate model accurately. If you use 5 observations to estimate the regression line, then the estimates are not reliable. Then we have larger test set. So tests performance can be evaluated more accurately, but the original estimates are not good. So it's almost nonsense. So either way, it does not work well. So maybe 50-50, or typically we have a slightly larger training set, for example, the 2/3 or 80%. It really depends on the sample size and but if large enough sample size, probably 2/3 of observations in a training set. But at least we have the trade-off. Yeah. And also the randomization. So training set and test set should be randomized, but this randomization has a lot of the variability. So this is the test error. Yeah, so test error. So we evaluate the error size by the test set with one training and a test set. Okay, so just the training set is here. Okay, maybe I would say that okay, so suppose n is equal to 10 and a training and a test, and a training set, maybe the first observation and the second, third for maybe the 7th, and the test data set maybe half and half, okay, 6 to 10. Then test performance. Okay, so this is the polynomial regression. So training set. Okay, so we have the y is equal to beta naught plus beta 1x plus maybe beta 2x square plus up to beta k, the beta k x to the k's power plus epsilon. So we estimate several the models depending on k, and we think about the k and the test error. Then if the k is larger, the test error is slightly smaller. But if we use different training and test set, the situation is different. So suppose that we have for different data set, so this one, maybe training set is maybe the first observation and fourth and the seventh and ninth and 10th. And the test data set is maybe second, third, and fifth, and sixth and eighth. Then we have different estimated parameters and the different test error size. So in this case, it's much different from this path. Okay. So the variability, it's really the variable. So the test error has a lot of variability. So that is another problem in training and test approach. So if you are doing science, we would expect that your result and someone else's results are the same, or at least the difference should be negligible. But here, just because of randomization to make training and test sets, that we have a lot of variability. So that is a problem. So that's why we have to improve this model. So one is that, so we want to avoid the variability. So the one is to avoid trade-off between the training set size and test set size. The second problem is to avoid the variability in training test division. Yeah. Then one ideal way to evaluate the performance is this leave one out cross validation. So suppose we have n observations in the entire data set, then we use the second to nth observation as training set. Sorry, maybe we have, training set is blue always. Okay, so this is training set, and the test set consists of just one observation. So this is the test set. But okay, so then we can calculate the error size. Maybe I would say just E1. And then the next step that we do the training and the test approach again, training validation set approach again. So next, in the second time, the training set is the first observation and the third to nth observation. And test set is just second observation. Then we evaluate the error. Maybe error size is E2. And so on. And we just make this n times. So we do the n times of the training and so validation set approach and evaluate the performance. Then we can exactly get the one error for each observation. So from the first training and test sets, that we get the error for the first observation, and from the second set, the error for the second observation, and so on. And if we think about the total error size, for example, the sum of maybe the EI square, I is equal to 1 to n, maybe we divide by n, then this is good because we evaluate all error just for once for each observation. So we don't have any randomness caused by the training and test set division. So this is the leave one out cross validation. But if we have, for example, the 1 million observations, this is not feasible because we have to do this 1 million times. 1 million times. It may be possible if you do just the simple linear regression, but at least it takes too much time if you are doing a complicated model. Suppose that each model is estimated in 5 seconds, then if you have the 1 million observations, then you need the 5 million times, 5 million seconds, right? So 5 million seconds, that is, I don't know, maybe 2 months. So that is too long. But at least this is ideal. At first, the training set is large enough, right? So training set is n-1 observations. So it almost replicates our, the entire sample. So in terms of the reliability of estimates, it's the same level as using the all observations. That is one good thing. And also, each observation is used as our, the test observation. So it's good. Each observation is used once in a test data set. So we don't have any variability about the selection of test set. So it's very good, but it takes time. So that is the problem. Yeah, so this is the concrete procedure. So suppose we have the x1, y1 to xn, yn. Then leave one out cross validation, split the data into the training set with n-1 observations and the test set with 1 observation. Then suppose that the xi, yi is the test set. Then we estimate the model with training set. That means the all observations except xi, yi. Then we predict yi by that model. And suppose the prediction is yi hat. Then we calculate the squared residual. So yi minus yi hat square of this. Then we take the average of this. So basically, we repeat this for all i's. Then we take average of this. Mean of MSE. Sorry, what's this? Okay. So then we can evaluate the error size. Yeah, so training set is large, so that's good. Training set is small. That is often the problem, especially that you have the scarce variable. For example, that you have the 500 observations in a real estate data, and the one column. Okay, so suppose the x1. X1 is the variable indicating the swimming pool. Okay, then suppose that we only have 3 observations out of 500 houses which have the swimming pool. Then if you have 250 observation as a training set and 250 observation in a test set, then maybe all observations with the swimming pool, all 3 observations in the swimming pool are in the test set. Then, of course, we cannot evaluate the effect of swimming pool in the training data set. So you will make an error. So basically, we have the variable, the predictor variable, whose value is all 0 in a training set. Then we cannot estimate the coefficient. So often it makes an error. But if training set is large, then we can avoid that kind of problem. Yeah. Yeah, so that is the identification problem. Yeah, and also that there are no randomization in the leave one out cross validation. And the problem is the computational burden is large. And for some specific models, we have a shortcut. We have shortcuts to get the leave one out cross validation. For linear regression models, we have a shortcut. And actually, the training error, the test error for nth observation is calculated by this quantity. And here, yi hat, this is the predicted yi, where the model was estimated by all observations. And hi is defined by this quantity. Then the cross-validated error is calculated by the summation of this. So this really takes a short time because we fit only one model. So leave one out cross-validation. In principle, we have to run regression model n times. So if you have 500 observations, then you have to estimate the model 500 times. At first, you use the second to 500th observation. The next that we use all observations except for second observation, and the third time that we use all observation except for the third observation and so on. So 500 estimation. But here we only have one estimation because this yi hat is estimated. Yi hat is defined by the predicted yi, where the model is estimated by all observations. So we only have to estimate the model once by all observations. So it's very quick to calculate it. Of course, we have to calculate this quantity, but that isn't really takes too much time because we just take the average of 500 numbers. Yeah, but this is just true for linear regression only. So linear regression, if you do some algebra, you can derive this kind of convenient formula. But for more complicated models such as logistic regression, we cannot do that. Yeah. Do you have any questions for leave one out cross validation? Yeah, so practically, yeah, go ahead.
So what would be the max, say, number-ish that you would use like the full leave one out?
Observations. Yeah, I think the short answer is that I almost never use it. So this is conceptually the best one. So if we only have, for example, 30 observations, 40 observations, maybe 50 observations, even 100, it's fine. But the larger than that, I would suggest the k-fold cross validation. And also, it really depends on the model. If model is simple, then you can do 1,000 times, for example. But if model is complicated and each model takes, say, 3 minutes to estimate, I don't really recommend this method. Even 100 observations, it takes 300 minutes. So the short answer is almost never used it. And yeah, but the situation is that it really depends on how simple the model is. The simple model, we can do that. And the complicated model, we never use it. And usually we use this k-fold cross validation. So that means basically the 1 over k of total observation is in a training set. And the remaining one, so that is k minus 1 over k test set. For example, if n is 100 and k is 10, training data set, we have 10 observations, and the test data set, 90 observations. So we have some randomness about how to divide the 10 to 90. But this is cross validation, so that we repeat this, actually repeat 10 times. I think the 10 is maybe not a good example, so maybe I would say 5. Okay. Then we use the 20 observations because the 100 over 5, and here 80 observations. But the k-fold, so we have the 5 times. So just the concept is that each observation should be in the test set only once, exactly once. So the next time, the next 20 observations are in a training set, and the next validation, then we have the next 20 observations. And of course, these 20 should be randomized. So basically, we randomly divide 100 observations into 5 groups with the equal size. Then we use just one of those as the test set and the other 4 as the training set. And we repeat that 5 times. So this is k-fold cross validation. So how much time does it take compared to just the usual validation approach? So this is k-fold. So actually the k times more time we need. So five-fold cross validation, we need the 5 times as much time as the one simple validation approach. So 5 times. 5 times is fine, right? So it's a fixed number. It's good. leave one out cross-validation, the n times more time to compute. So, and it really depends on the sample size. So this is good. It's not too computer intensive. Yeah, so to be exact, the k-fold cross-validation divides the dataset into k-equal groups randomly, and they use the ith group as the test set and the remaining k-1 groups as the training set, and evaluate the MSE, mean square error. Say that this MSE sub I, then we repeat this for all i's, then take the average of this MSE sub I. So I almost always recommend this, the k-fold cross-validation. And maybe the common choice is k is equal to 10. Some packages in R uses the k is equal to 10 as default. And this number, usually people don't care too much about it. So you can choose arbitrary number. So at least k should be 2, and at most n. So k is between 2 and n. So if it's really computer intensive model, that you can use k is equal to 2. If not, maybe you can use just k is equal to 10. And if it's very quick, maybe you can get even larger k. Any questions about concepts of k-fold cross-validation? Okay. And several the graphical examples here. So at first, this is the simulated data, and the true trend line is this black line. And this is simulation, so we add some noise on this, and those are the black circles. Okay. Then we fit the 3 models, the yellow one and the maybe too much, yellow one and the blue one and the green one. Okay, so these are different models. So yellow one that you can see, this is just linear regression, and the blue one is degree 5 polynomial. So this is straight line. So this is the y is equal to y is equal to, the a plus bx or something, and this one is the 5-degree polynomial. So y is equal to b0 plus b1x plus b6, maybe b5, maybe b4x to the 4th power. And the green one is the more flexible model. Actually, we have the 20, maybe 2 parameters, 20 parameters. So this is y is equal to beta naught, b1 naught, bx, b1x plus up to b20x to the 20th power, plus epsilon. Okay, so then we have the 3 models. And the training error is always smaller for more complicated model. So this model is more complicated, more parameters. So always training error is smaller. So actually the graph becomes this training error. So training error is just that we are thinking about the fit. So x1 to suppose maybe x100 and x101 to x200, and suppose these are randomized test set and the training set. And we have y1 to y100. Then we estimate the model from this set. Then we estimate the y1 hat to y100 hat. Then we can calculate y1 minus y1 hat square and up to y100 minus y100 hat. So this is not really the fair prediction. So we use the data set, this data set, and we just evaluate the performance on the same data set. So it's the situation that we know the answer and we predict the answer. So it's not really true prediction. So then the average of this quantity is training error. And the training error is always smaller for a larger model. But the test error is different. So we have the y101 to y200. If the model is unnecessarily complicated, if you estimate the model, this is based on these estimates, then y101 minus y101 hat, y101 to y200. So these errors is a kind of real prediction. So if we take the average of this, that is the test error. Okay. Test error gets larger if model is unnecessarily complicated. So you can see that the blue model is the best among these three. And you can also see this in the graph. That you can see the yellow line is too simple to represent the truth. And the blue line is somewhat reasonable to represent this true trend X, through the trend of the black curve. And the green one, it fits the data well, but it's too volatile to express the truth. So it's good to fit the training set, but for the test set, actually it performs worse than blue one. So it picks up more noise than the blue curve. Yeah, so the complicated model always have smaller training error, but often have larger test error.
So quick question on that.
Yep.
So would that mean that when the model that we use is like less complicated, so if we use the y equals a plus bx plus e, would that mean that it would have the best test error because it doesn't pick up on noise like?
No, actually, okay, so it's good that's not picking up the noise, but it's too simple, so it cannot represent the truth. Yellow one.
Okay,
so
so like
this
theoretically,
right,
it would be like the best for error or for noise. So it's like.
So yeah, so it picks up less noise. In that sense, it's good. So noise is small, or we can say the variance is small. But we have a large bias. You can see that it cannot represent the larger error around here. I mean, it cannot represent. It cannot estimate the this curvature, the truth by this yellow straight line, right? So the deviation is large, so bias is large. Here also bias is large. So it picks up, so this simplest one that picks up less noise, the least noise among these three, but the error size is larger than the middle one because it cannot express this curve. Or we can say that we have larger bias around here or around here or around here.
Okay, thank you.
Yeah, so maybe in short that we have, okay, so 3, 1. So this has 2 parameters, 5 parameters, 21 parameters. So number of parameters, 2 and 5 and 21. Okay, so the variability or variance. So this is the smallest. This is in the middle. And this is large. And bias. This is large because it cannot represent this kind of curve. This is in the middle. This is small. And in total, actually, this is smallest. And from this, maybe this is the second smallest. And this is large. Okay. So the point is that we have to minimize the total error. So basically, the middle one is the best. Middle one, the balance, the variance, bias, and the variance well. It has smaller bias and it has a reasonably small variance. So in total, it's most accurate. Okay.
That makes sense. Thank you.
So the same thing for the second one. So this is maybe more practical situation. So it looks like the relationship is almost linear between x and y. So again, the black one is the truth. Black curve is the true curve, and the black circles are simulated observations. And we estimated the three models: the yellow one, the blue one, and the green one. So green one fits the data best, bias is small, but the yellow one is the smoothest. So the variance is smallest. And when we check the training error, then always the larger model has smaller training error. So degree 20 polynomial fits the best. But for the test set, test error is actually the worst for the most complicated model. And it's not clear, maybe this one or this one. Probably this one is slightly better. So this is, I think, the 3. So 3 observation is probably the optimal for the model. I don't know how they make this the smooth curve. Probably they tried other things. This is simulated model, so probably they make some theoretical curve, and then they connected the theoretical curve for each number of parameters. Okay, so anyway, so the blue one is the best. So there is some optimal location. So optimal the flexibility, or optimal the number of parameters, or model complexity. So if model is too complex, it's not good, but too simple, also it cannot represent the truth. Yeah, I mean, in a common sense, probably the transformation of y makes more sense. Maybe I would say the y square root, or maybe something, maybe makes it better. But yeah, but in terms of this polynomial regression, the optimal flexibility or number of parameters is 3. And example 3, the true line is again the black one. Probably this is cubic curve. And we fit the 3 models. The straight line and the blue one is the degree 9 polynomial. And the green one is degree 20 polynomial. What's the best? And actually, the test set, the training set, larger model is better, but for the test set, test error, that you can see the middle one, the blue one is the best. So they always have some optimal point to minimize the test error size. Yeah, so this is the from the examples, the 3 examples in the previous slides. And the blue curve is the true error rate. So this is simulation. So kind of the expected error rate, expected error size. And the black dashed curve is the leave one out cross validation. So it is most computationally expensive method. And orange curve is the tenfold cross validation. So it takes less time. And you can see the black dashed one and the orange one are almost always similar. So leave one out cross validation and tenfold cross validation almost have the same result. So tenfold cross validation is much faster. So why we don't use it? So usually we use the tenfold cross validation or fivefold or whatever. But the true expected error rate is different from this. So these ones are similar and these ones are similar, but this one actually our cross-validated error is much smaller than the expected error size. Why? So this is because of luck. Okay, so we are lucky. We are lucky to divide training set and test set. So if our trained model really fits well for the test set, then this can happen. Or we can say that probably the problematic observations are all in the training set. So in the training set, we have the something, some observations are not really interpreted well, but in the test set, all observations are pretty normal. So we have the small test error always. So just we are lucky. We are lucky. And if we are lucky, then often the error size is even smaller than the truth. So that is the case. But the leave one out cross validation also have the very small error. So I don't know why this happened. Yeah, tenfold cross validation often just it's small because of we are lucky to divide training and test set. And leave one out cross validation error small. Usually that means the error is really small. But yeah, I don't know what happened here, but the just point is leave one out and tenfold cross validations are similar. And how to choose k? So it's not really serious problem. So best one is k is equal to n, but it takes too much time. So usually 5 or 10 is fine. If you do final project, just use 5 or 10, or you can even use 2 or 3. And large k gives a smaller bias to estimate the test error. Yeah, so because yeah, so it's a little bit difficult, but so if k is small, then large case, yes. So if k is large, then we use most observation as a training set, right? So if k is equal to 10, then 90% of observations are in a training set and only 10 observations in the test set. So if we use 90 observations, then we can avoid most problems. So it's very similar situation to using all 100 observations. Yeah. Yeah, I think this slide is a little bit hard to interpret. Yeah, so this yeah, I think that this one and this one maybe just a little bit more technical. So in some models, if the sample size is large, we suffer from overfitting. So that is true for some tree-based method and some neural network. So large sample size often suffer from overfit. So the larger K means that we have the larger training set. So we train it well. So bias is small, but variance is large. But largely we can ignore this for usual regression analysis. Yeah, so just the point is that larger K takes more time, and that is one point. Yeah, and the k-fold cross-validation, it has some randomness. So sometimes you can try several times. For example, the 10-fold cross-validation 3 times. Then we have 3 MSEs. First one, 10.1, second one, 9.8, third one, 10.2. Then you can evaluate how reliable this MSE is. So sometimes it's useful to calculate the 10-fold cross-validation several times. 10-fold cross-validation 20 times, for example. Then you cannot be lucky, basically. So the results should be almost the same as another person doing the same simulation. So even if we do 10-fold cross-validation time, still in total you have to try 200 times. So if you have 1 million observations, it's much quicker than the leave one out cross-validation. Yeah, in some statistics class that I asked students to do the 10-fold cross-validation 20 times and to report the mean and the standard deviation of MSE, so that we can compare the performance of the model. Yeah. Yeah, actually, I think the last year, I asked students to do some prediction for the Boston dataset, I think, Boston dataset. Then one student performed very well, and he developed the model with very small test error. So he wasn't really the best of the best students in the class, but for that prediction modeling, he is far better than any other people, including me. So I think the different people have different skills. So some people are strong in mathematics, and some people are strong in coding, and some people are really good at dealing with the data. So even if you are good at numbers or mathematics, then you further have to think about what's the best skill compared to others. Yeah, and cross-validation for classification problems, basically we can do the same thing, but the one observation only have limited information for classification problem. That is whether you make a mistake or you got the correct answer. Yeah, so this is one example of the cross-validation for classification setting. So we regress the response variable on the polynomial of x1 and x2. Yeah, often including higher order terms to solve many questions. So for the Boston dataset, I compared several different models. I think that I compared all models in this textbook, and the more advanced models are better than the logistic regression or linear regression. But actually, if we include these terms, the higher order terms, and also sometimes the interaction terms, x1, x2, or x1 square, x2, and so on, actually it performs better than other models, such as support vector machines or tree methods. So to improve the model performance, these higher order terms are especially important, especially the square term, the cubic term, and so on. So okay, so we compare this model for k is equal to 1, 2, 3, 4. So we want to compare the test performance, the test error size of these 4 models. So here is the graphs for those 4 models. So this is k is equal to 1 and 2 and 3 and 4. And the purple one is the true boundary. This is based on simulation, so we know the true boundary. So in this chapter, the truth was given, but that is because we are doing simulation. In the real data analysis, this is unobservable. Analysis, not observable. So this is a kind of demonstration purpose. And the boundary obtained by these 4 models are this black. Logistic regression with only linear term, so boundary is linear. So that is straight line, and cubic the degree two that we have more complicated curve, and the degrees 3 and 4 more and more complicated curve. And these are the simulated observations. And which model looks the best? Yeah, so basically the error happens for the discrepancy between the purple curve and the black curve. Okay, so actually for the observation slightly different, but these areas, these are basically errors. So error is smaller when, slightly smaller when we get k is equal to 2, and much smaller for k is equal to 3. And 3 and 4 almost looks the same. So probably the 3 or 4. So these are better than k is equal to 1 or 2. And actually they go more. So the 1, 2, 3, 4 up to 10. Then yeah, the training error is blue. This is training error, and the test error is brown, and this is cross-validated error. Test error. Sorry, I think probably this is not so. The black one. I think that this is the truth. This is the test error by CB, and this is training error by CB. So training error gets smaller, basically. No, not really. Blue, training error CV. Yes, the training error. Training error usually gets smaller if the polynomial order of polynomial gets larger. And why we have this bump here? 4, 5, 6. So larger one, training error is smaller. Larger. Oh yeah. So this is logistic regression. So that we optimize the likelihood, right? So the likelihood function is optimized, but the error is counted by the error rate. So it uses different measures. So that's why we have the bump. So usually the training error always gets smaller when model is more complicated, but the model is estimated by maximum likelihood, but we evaluate error by error rate. So the number of errors, the proportion of errors. So that's why we have some discrepancy here. But as a tendency, the blue line always going down. And the test error is going up from maybe 3 to 4. And actually the truth is the best at the k is equal to 4, but actually the k is equal to 3 has the smallest test error. So if we use cross-validation, we choose k is equal to 3. And actually it's not correct, but it's close to the truth, k is equal to 4. Do you have questions so far? So cross-validation is really good when we determine the model. So in real data analysis, the truth is unobservable. Because real data usually does not come from the simulation, but without the truth, that we can choose a good model by cross-validation.
Sorry, Professor.
Yep.
I have a question.
Yeah.
I didn't understand the last part. You said why we have the bump there between 6 and 8. Could you please repeat that?
Yeah. So because of the difference in the model performance. Okay. So the larger model has better fit in terms of MLE likelihood. But not necessary for the error rate. Okay, so suppose k is equal to 4 and 5. Likelihood, maybe k is equal to 4 has higher likelihood. I don't know the unit, but okay, likelihood is okay, negative 4.1. And here, likelihood is negative 3.9. Okay, so likelihood is better here. But the error rate is different issue. Error rate, maybe this one is 0.39 and 0.41. Okay, and error rate may be smaller for this because we have two different criterion. So if likelihood is higher, usually the performance is good, but the error rate is based on the 0.5 threshold, right? So even a better model that can have lower error rate. Maybe to make specific example, suppose the k is equal to 4 and 5. And we have four observations. We have observation 1 and observation 2, observation 3, and observation 4. And the truth is y is equal to 0, 0, 1, 1. And the predicted probability k is equal to 4, maybe 0.4, okay, and 0.45, and 0.55, and 0.6. Then all decision is correct in terms of 0.5 threshold. But if k is equal to 5, then we may get a better prediction, such as, okay, so this is 0.05, and this is 0.1. Okay, then this is maybe the 0.49, and this is 0.9. Okay, so in that case, probably the higher likelihood for k is equal to 5, but the k is equal to 4 has lower error. Okay, so in terms of likelihood, the k is equal to 5 is good because the truth is 0 and the estimated probabilities are pretty close to 0. and 1, and pretty close to 1. But we barely missed this one. This one, because 0.49 is less than 0.5, so we missed this prediction. So error rate is 25%. K is equal to 4. Almost always, it's the probability is close to 0.5, so it's not really a good prediction. But we are lucky that these two are less than 0.5 and these two are more than 0.5. So actually, error rate is 0. So this kind of thing can happen.
Thank you, Professor.
Sure. Okay, so Bootstrap. The Bootstrap is a method to estimate distribution of parameter estimates with multiple sampling from the dataset. Yeah, so suppose that we have the n independent observations in the sample, and we want to estimate a parameter alpha. For example, the population mean or population variance or slope of regression or any parameter. And we randomly sample n observation with replacement. So originally we have n observations, but we allow the replacement. So take the specific observation more than once. Then we randomly pick up n times. Then we can kind of make some randomness in this sample. And still, the number of observations, we can keep the same number of observations. And they calculate the parameter, estimate the parameter based on this randomly selected n observations. Then repeat. Okay, so then we can have one estimate, right? Then we estimate this many times. I would say the 300 times. I think some paper mentioned that n is equal to 200 or 300 are sufficient to see the result. If you want to publish a paper, maybe you can repeat it more at the final stage, maybe 10,000 times. But maybe for the beginning, n is equal to 300 is a good size. And make a distribution. So we estimate the same parameter again and again with randomized sample. Then we can, maybe I would say hat. Okay. Then we have the alpha hat, distribution of alpha hat. So we can have a distribution of alpha hat. So you can think about just the mean of alpha hat or variability of alpha hat or distribution of alpha hat we can get. Then we can calculate the variance of alpha hat by the sample variance of these alpha hats. Yeah, sampling with replacement is this. So suppose that we have 5 observations, 1, 2, 4, 8, 16. So what happens when sample the 5 observations with replacement? Then the one realization is this, the 2, 4, 1, 4, 8. So 4 has been picked up twice, and 16, the 0 times. So we have some randomness in this. And we repeat the same procedure. Then next time we get 16, 8, 4, 4, 4. So in this way, we can have the randomized sample. And still, we have the same number of observations. So since we want to estimate the variability of alpha hat, and the sample size really matters. Usually, the sample size is doubled, then the variability gets 1 over square root of 2 times the variability of the the smaller sample. So it's important to keep the sample size. So we allow replacement, but still we sample the n observations from n observations. Yeah, example. So we have 5 observations, and we want to calculate the mean, and we want to know how reliable that the sample mean is. So this is the vector x, then sample mean x bar is here, and this is just the standard deviation of x bar, standard deviation of x, sorry, standard deviation of x. Okay. Maybe s sub x or standard deviation of x. And yeah, so if you have studied statistic, you know that the variance of x bar is equal to standard deviation divided by square root of n. So that is 0.6148 divided by square root of 5. So you can get this number. But we can almost replicate this number by Bootstrap. So that means that we sample out of this x, sample 5 observations out of x. We can use this sample function with replace equal to true. Then we store that in vector m. Okay, so we create the m. So this is 100 numbers, the space the space to store the 100 x bars. So we calculate x bar 100 times. So we have the x bar 1, x2 bar, x bar 2, x bar 100. Then we check the distribution of this. And actually the standard deviation of this is 0.2549. So it's slightly smaller than 0.275. The 1, that's because of randomness, and 2, actually we only have 5 observations, so still we have some bias. But anyway, so the number is pretty similar to this, and this method works well when we have moderately large sample size. For example, if this has the 10 observations, x has 10 observations, then this is much closer to this truth. Yeah, so the point is that for this specific question, we can estimate standard error of x bar by this formula. But in general, this kind of theory is difficult. So this is very simple situation that we just have n independent observations and take the sample mean. But if we do linear regression or logistic regression and we estimate parameters, and maybe the some observations come from the same individuals or something, if the situation is more complicated, then usually we don't have the theory to calculate standard error of the estimated parameter. So the Bootstrap is a very strong method to get the approximate the value of standard error of the parameter estimate.
Sorry, Professor.
Sure.
When we use LM function in R, does this function use Bootstrap for estimating betas, because we have betas, mean of betas that we consider as coefficient, and also we have a standard deviation of betas, and also, I don't know, we assume that they have student distribution.
Actually, the LM function uses the theoretical method to calculate standard error. So LM function in R, the variance of beta hat is estimated by the sigma hat square times the model matrix X transpose to X inverse. So it's calculated analytically. So it's similar to this way.
Okay.
So you can calculate. Yeah, you can use the Bootstrap method, but the LM function in R uses more exact method, more exact mathematical theory to calculate the standard error.
Oh, okay, thanks.
Yeah, and I think the Bootstrap, probably the most popular, most common application is the linear regression with correlated observations. we will see. But if linear regression becomes a little more complicated, then we have to use Bootstrap. Yep. Yeah, so this is actually the so your question actually is discussed in this slide. So if we have the data set, original data set, and suppose that we want to estimate the parameter. So I think that this is the model estimates the parameter of y is equal to alpha x. We don't have intercept here. And what's the standard error of alpha? Then by bootstrapping that we can use this, we can estimate the Bootstrap can estimate the standard error of alpha hat. And how to do that? So we bootstrap. So we take 3 observations out of these 3 out of the original 3 observations. Then we estimate alpha hat. And we have another bootstrap, 3 observations. Actually, this is the same as original data set. Then we estimate this. And another data set, then we estimate this. Then we have the distribution of alpha hat. Then we can estimate the standard error of alpha hat. The standard, maybe the mean is here and the standard error is here.
Sorry, Professor, but the observation are all are the same. These are some difference their orders, but the observation X and Y's are same.
Yes. So only randomized part is that this part. So we have the different the different set of observations. So the different choice of observations. Each observation is the same as the original data. So this is the similar situation as this. So suppose we have 100 observations. Okay, so we estimate parameter alpha hat. And sometimes we are not sure if this alpha hat is correct or not. Okay, so maybe we just drop several outliers and we see whether or not alpha hat changes. So we are doing that kind of the method. Okay, so we just add some randomness in a data set, then we see how much the result changes. Yeah, so again, so the observation itself, it doesn't change. The first observation is here. And the second observation here. So observation itself does not change. Just the choice of observations are different. So. Oh, sorry, it's already 8:19. So but okay, so this is the last slide. So yeah, so this is a typical application of the Bootstrap. So suppose that we have 200 observations for response time to the signal and the alcohol content in the blood. So basically, if people consume more alcohol, then they are slow to respond to a signal. And we want to fit the model y is equal to alpha plus beta x. But suppose that we only have 82%. So some people are measured repeatedly. So maybe some people are measured maybe 3 days in a straight. But some people are just measured once. Okay. So in this case, the assumption of the IID assumption of the linear model is violated. Right? So the linear model, we calculate the standard error of beta hat by theory, but it is based on IID assumption of observations. But here, some observations come from the same person, so this assumption is violated. So in such a case, that we can use Bootstrap. And the point is that we sample from independent observations. So here we can say that the 82 persons are independent, but the 200 observations are dependent. Some of them are dependent. So we have to sample 82 persons from the original data set. Not the we sample 200 observations. We sample 82 persons. So that means possibly the number of observations is 205 or 194. Because different persons have different number of observations. Then for each the resampled data, each bootstrapped data, we estimate the beta. Then we can make the distribution of beta hat. Then we can calculate the variance of beta hat. So this is probably the most common application of Bootstrap. So if data structure is complicated as this, then certainly the Bootstrap helps to estimate the variability of beta hat. Sorry that I extended the lecture time. So maybe next time I have to finish 5 minutes earlier.